Okay, we're going to go ahead and fill out the notes for today. We're going to talk about sum and difference formulas, and you'll see up here that I have them listed out for sine, cosine, and tangent. Now, the letters that we have in here, those are completely arbitrary, meaning I could have used any letters. I could have used X and Y. I could have used a regular A and B. I just happen to use the Greek alpha and beta symbols. It doesn't matter. Recognize that there's a pattern to each one of these formulas. So for the sum formula, the sine of alpha plus beta is going to be the sine of alpha cosine beta plus cosine alpha sine beta. And if you just recognize the formula, the sine of the sum, sine of the first, cosine of the second, plus cosine of the first, sine of the second. Similarly, the sine of the difference would be sine of the first, cosine of the second, minus cosine of the first, sine of the second. So if you just refer to where they are in the formula, alpha being the first one, beta being the second one, you can see the pattern as it develops through the sine, cosine, and tangent sum and difference formulas. The common mistake that people make is that they assume you can just distribute the trig function to the two angles. So let's say I have angles alpha is 30 degrees, beta is 60 degrees. And I asked you to find the sine of alpha plus beta, right? And I substitute that in. If I substitute it in, then I'm doing the sine of 30 plus 60, which would just be the sine of 90. And we know that the sine of 90 is 1. A lot of times, though, what people do is they say, oh, well, if I'm doing the sine of alpha plus beta, isn't that just the sine of alpha plus the sine of beta? People automatically see parentheses and they think distribute. Well, let's see why that's incorrect, right? Alpha was 30, beta was 60. So I would be doing the sine of 30 plus the sine of 60. I know from my right triangle, special right triangle, my 30, 60, my very poorly drawn 30, 60, 90 right triangle, that the sine of 30 is 1/2, and the sine of 60 is root 3 over 2. That clearly does not equal 1. That would just be 1 plus root 3 over 2, which does not equal 1. So you cannot just distribute the trig function to the two angles that are in the parentheses. Okay, you have to follow the formula. If I went and followed the formula, I should get the same answer that I have here. If I follow the formula for the sine of the sum, so if I do sine of 30 plus 60, I'm doing, if I follow this formula, I'm doing the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. So let's see how that works. The sine of 30 is 1/2. The cosine of 60 is root 3 over. Cosine of 60. Sorry, cosine of 60 is 1/2. Cosine of 30 is root 3 over 2. And the sine of 60 is root 3 over 2. Right? I got that all out of my right triangle here. 1/2 times 1/2 is 1/4. Root 3 over 2 times root 3 over 2 is 3 over 4. 1/4 and 3/4 is 4/4. 4/4, which gives me 1. That's why the formula works. So let's go ahead and try a couple of examples. In this particular example, it says find the exact value of. Okay, that means they want it left in radical form. They don't want a decimal approximation. You also notice that the angle is in radians. You have a couple of options as to how to do this. A lot of people find it easier to think of this in degrees because if we're talking about exact value, the only angles we can use are 30, 60, and 45 degrees, or some combination of those. A lot of people find it easier to use those numbers as opposed to radians to figure out how we're going to manipulate the formula. So let me show you what I mean. If I convert 5 pi over 12 into degrees, I have a couple ways I can do that, right? I can just multiply by 180 over pi and convert that into degrees, right? 12 goes into 180 15 times, right? So that would be 15. And 5 times 15 is 75. So 5 pi over 12 radians is equal to 75 degrees. Now, using combinations of 30, 45, and 60, I could come up with a way to get 75. Again, they're looking for the exact value, so I can't just plug sine of 75 into my calculator. That's going to give me a decimal approximation. So I need an exact value. Well, I have a couple of options, right? But I think it looks like the easiest option actually for this one would just be to add 30 and 45. This one we don't really have too many options for, so we're going to go with 30 and 45. So instead of writing it as the sine of 5 pi over 12, what I'm really doing is the sine of 30 plus 45. But because our original problem is in radians, we want to make sure we carry radians all the way through the problem. So 30, if I were to write that in radians, 30 goes into 180 6 times. So 30 is pi over 6 radians. 45 goes into 180 4 times. So 45 is pi over 4 radians. And so pi over 6 plus pi over 4 would equal 5 pi over 12. If you got a common denominator and added those, you get 5 pi over 12. Now I can apply my formula. My formula for the sine of the sum, sine of the first, cosine of the second, plus cosine of the first, sine of the second. So sine of the first, sine of pi over 6, times the cosine of the second, plus the cosine of the first, times the sine of the second. I know the right triangles, the 30, 60, 90 right triangle. So again, if you don't remember it, you can always recreate it.
That is not my area. I'm not sure.
Or the 45, 45, 90 triangle, we can always recreate that as well. And then we can pull our values right off of our triangle if we don't know them. Right, so the sine of pi over 6, or the sine of 30,
What's your next problem?
is 1/2. Cosine of pi over 4 is 1 over root 2.
And what kind of sneaks do you do?
Cosine of pi over 6, the cosine of 30 would be root 3 over 2, times the sine of pi over 4 is 1 over root 2. If I simplify that, I have 1 over 2 root 2 plus root 3 over 2 root 2, which gives me 1 plus root 3 over 2 root 2. Remember, we typically don't leave a radical in the denominator, so we're going to go ahead and rationalize it, which means I'm going to multiply the top and the bottom by root 2. So in the top, that gives me root 2 times 1 plus root 3. Root 2 times root 2 is 2, times that already existing 2 would give me 4. You can leave it like that, or you could distribute that root 2. That would give you root 2 plus root 6 over 4. That is an exact value. let's go ahead and try another example. So pi over 12. 12 goes into 180 15 times. So pi over 12 I know is going to be 15 degrees. So again, I can use some combination of exact values that I know. So some combination of 30, 45, and 60. So I could either do 45 minus 30 because that would give me 15. Or I could do 60 minus 45 because that would also give me 15. Doesn't matter which one you choose to do. This time I'm gonna do cosine of 60 minus 45. Right, so that is going to be the cosine. Let me do it in radians. That's going to be the cosine. 60 degrees, 60 goes into 180 3 times, so 60 would be pi over 3. 45 degrees is pi over 4 in radians. If I go back to my formula, I'm doing the difference of the cosine. Okay, so I'm saying cosine of the first, cosine of the second, plus I have to go to the bottom sign here because I'm using the bottom sign there. So cosine of the first, cosine of the second, plus sine of the first, sine of the second. Okay, so cosine of the first, cosine of the second, plus sine of the first, sine of the second. Go back to your special right triangles. Okay, so the cosine of pi over 3, the cosine of 60 is 1/2. So I've got cosine of 60 is 1/2. Cosine of pi over 4 is 1 over root 2. The sine of 60 is root 3 over 2. The sine of pi over 4 is 1 over root 2. And again, this works out very similar to what we had before. Actually, I think it comes out to be the same answer. 1 over 2 root 2 plus root 3 over 2 root 2. Oops, 3 over 2 root 2. So that's 1 plus root 3 over 2 root 2. And again, we would rationalize that, multiply the top and the bottom by root 2. So you'd have root 2 times 1 plus root 3 over 4. And again, you can leave it like that, or you can distribute the root 2. Okay, we will finish up the notes in the next video. Thanks, guys.